A metasurface alters light polarization, virtual touch helps the blind, hydrogen prevents optical fiber damage, and light measures surface vibrations. That's this week on Light Matters. Hi, I'm James Lowe, and this is Light Matters for August 20th, 2014. An ultrathin metasurface can alter light polarization with 50% efficiency, which could lead to the development of microscale devices for controlling light. A team from the University of Michigan and its Lurie nanofabrication facility created the device, which has a surface area of 250 square microns and is 400 nanometers thick. The metasurface is composed of three 28 nanometer patterned gold sheets that are fabricated using electron beam lithography and separated at sub-wavelength intervals by dielectric substrates. The researchers have found that when right-handed circularly polarized light enters the front of the metasurface, it emerges on the opposite side as left-handed circularly polarized light. When the operating optical wavelength is 1.5 microns, the transmittance from right to left polarization is 50%, and the extinction ratio is 20:1, which the researchers said represents an order of magnitude improvement over previous optical structures exhibiting asymmetric transmission. Such metasurfaces in the future could be used to control light's phase and amplitude. The research was published in Physical Review Letters. An IR sensor and the concept of virtual touch could help the visually impaired take on many day-to-day activities more easily. Researchers at the University of Cincinnati used an inactive torch, which is a tactile feedback device for experiments in sensory substitution, in tests to help visually impaired subjects navigate through doors. The inactive torch device uses two infrared rangefinders, one that covers an outward range of 8 to 80 centimeters, while the other covers 20 to 150 centimeters. When the device detects objects in its path, it vibrates through an attached wristband. The intensity of that vibration increases as the device gets closer to the object, allowing the user to judge how to react. The Cincinnati study involved subjects with normal or corrected to normal vision. They were asked to make perceptual judgments in three ways, using only their vision, using a cane while blindfolded, and using the inactive torch while blindfolded. The researchers found that the subjects' judgments in all three tests were equally accurate and functionally equivalent. Soon, the researchers will study more complicated judgments, including the subject's ability to step over obstacles and climb stairs, all while using the same three approaches. Hydrogen-fortified optical fibers are capable of sustained transmission of high-intensity UV light. A team from the National Institute of Standards and Technology created the new fibers, which they say could help reduce errors in logic operations in quantum computing experiments. A combination of hydrogen infusion and curing with ultraviolet light appears to confer long-term resistance to damage, the researchers said. The fibers have low ultraviolet loss and also clean up misshapen light beams. Fibers with solid cores made of fused silica surrounded by lattices of air holes demonstrated the formation of a crystal structure that maintained the shape of transmitted laser beams. The fibers were infused with hydrogen gas at 100 times standard atmospheric pressure for 4 to 6 days. Once the hydrogen diffused into the fiber cores, the fibers were cured by exposure to ultraviolet laser light for several days. When used to trap ions, the fibers reduced stray light and fluctuations in the laser beam pointing, and allowed UV transmission between separate optical tables, according to the researchers. The research was published in Optics Express. A technique that passively monitors light intensity modulation is able to measure the physical and optical properties of a vibrating surface. A team from the University of Louisville, in conjunction with Spectral Sciences, Inc. and the U.S. Air Force Research Laboratory, used high dynamic range cameras with large focal planes to detect tiny changes in the surface normal of various objects. Small temporal modulations in the light scattered by vibrating surfaces are used to measure the vibrations. The technique can be used to produce an image of the changing normal without touching the surface or altering its state, the researchers said. It also can image any object to determine its vibrational properties with or without active illumination. As surface vibrations can be imaged at any scale, the technique can also work with microscopes and fisheye lenses. The research was published online by SPIE Newsroom. That's it for this edition of Light Matters. Email us with your questions or comments at lightmatters@photonics.com. And don't forget to follow us on Facebook and Twitter for news updates every day. Thanks for joining us. We'll see you again soon.